Hey everyone, let's talk a little bit about vector notation, and I want to get into dot products again. But a couple of things. First off, in your textbook, vectors will be noted with boldface print. When I print an exam or a quiz, I do the same thing. I generally put the vector notation as boldface, so keep an eye on that in the textbook. But when I write on the board or write on paper, then I'm going to use the arrow over the top of the letter. And there might be subscripts in here. Talk about that at a later time. But in Cartesian format, I have the I hat and the J hat. I just want to make a note that I hat is again a unit vector, has a length of 1, not 1 meter, not 1 inch, just 1. It has a length of 1 and it points strictly in the positive x direction. Some books will use E sub x with a hat over the top of that, and some books will use U sub x with a hat over the top of that. The critical thing here is that the hat is an indicator of a unit vector. In fact, we'll use that in arbitrary directions later on in this course as well. J hat points strictly in the positive y direction. Again, E sub y hat is common notation. U sub y hat is common notation. So I would write a vector out in Cartesian format. This vector A would have some component, some length in the x direction, and I multiply, this is just a length now, and I multiply that by I hat to indicate it points in the positive x direction. And then in the y direction, it has some length y hat, right? So it might be moving up like this, and that's going to point strictly in the positive y direction, which is the j hat direction, okay? So there's just some notation that you're going to come across. Okay, so let's talk a little bit about dot products. If I have two vectors, I have a green A and a purple B, hopefully you can see those colors, then A will have some notation. A will have some notation, A sub x I hat plus A sub y j hat, and B will be some B sub x I hat plus B sub y j hat. And we talked about this a little bit in a previous video. I know that the dot product of these two vectors, A dot B, is equal to A sub x, B sub x plus A sub y, B sub y. Notice there's no i's or j hats in here, right? Those are not there. This is a scalar quantity. I'm going to get a number, no direction, just a number. And we also learned that this was equal to the magnitude of A, which I'm going to write like this, right? The absolute value of A. And if I needed to, I would tell you then that the magnitude of A was equal to the square root of A sub x squared plus A sub y squared. That's the length of this green line, right? Now, it would be the Pythagorean theorem is what I've got in here. The x component and the y component. All right, and so then the length of B, and then the cosine of the angle between them, which I have indicated to put the Greek letter theta, right? So A times B times the cosine of theta. Oftentimes I will write this as AB cosine theta, okay? So keep an eye on that. I would write A and B to no arrows over the top. That's an indicator that I mean magnitude. And if this was printed, these would not be boldfaced, right? They would not be boldfaced. But this is more demonstrative. It really exaggerates that idea. But either one is good. And I'll probably do this more often than I do that. Why? Because it's faster to write. Very simple and straightforward. Okay, so take a look at this then. That's the dot product. And notice I've got cosine of theta. And so let me rewrite this a little bit as AB, A times B cosine theta. And if I do that, B times the cosine of theta, what I can do is I can drop a perpendicular here. So I'm going to make that black dashed line, light line if you will, is perpendicular to the vector A. And so if I do that, then B cosine theta is this length right here. Right, so this is B cosine theta. And so I sometimes will write this as the component of B, right? Not the x component or the y component, but the component of B along A, right? The component of B parallel to A, right? Because x and y are in this direction, but I could rotate those and B would still have a component along some rotated X and Y axis. So just think of this as that much of B that is parallel, that much of B that is parallel to the A. So I could write this as A, B parallel. Okay, so the dot product gives us some indications of the component of one vector along the other. Well, I did the component of B along A. Does the reverse hold true, the component of A along B? And the answer is yes. But if I dropped a perpendicular to B from A, you'll notice it doesn't touch the vector B. So what I need to do is I need to extend B, right? B is going to have this line extended. The length of B doesn't change. I just draw the line along the direction of B. When we talk about forces, we're going to refer to that as the line of action of the force B. So think of this as the line of action of the vector B. Right? If this is perpendicular right here, then A cosine theta would be this length here. So this would be A parallel. The component of A parallel to B. Again, this is A cosine theta. Right? But going back to this, it's AB cosine theta. That's just A cosine theta times B, right? This is all commutative. I can switch the cosine and the B around, and I get A cosine theta times B. So dot products give us components parallel to one vector to the other. Now, keeping that in mind, let's say two vectors are perpendicular, then there is no component of one vector parallel to the other because they're exactly at 90 degrees, right? Well, in addition, the cosine of 90 degrees is 0. So if your dot product, as you go through all of this process, remember that the dot product, A sub x, B sub x plus A sub y, B sub y, if all of this gives you 0, then you know that those two vectors are perpendicular. You know those two vectors are perpendicular. Okay? So keep that in mind. It's a very important aspect of a dot product, and we're going to take advantage of that later on, especially when we get into 3 dimensions. Right now I'm just talking 2 dimensions, but we're very shortly going to get into 3 dimensions. Okay, and then if I do 2 3-dimensional vectors, or 4 dimensions, 5 dimensions, doesn't matter. A little harder to figure in those dimensions or visualize. But if I go into multi-dimensions, if the vectors are perpendicular to each other, then their dot product will be 0. Okay, so we'll take advantage of that throughout the semester. All right, if you have any questions, please leave them in the comments below. Thank you.